Dear students, welcome to this digital lecture series. The topic of today's discussion is quantum mechanics, and in that we are going to see the Planck's law. We have seen that the classical mechanics failed because it was based on the concept that the material particles emitted or absorbed the energy in a continuous manner. That is, there was a continuous absorption or emission of energy by the material particles. Now, because of this, classical mechanics could not explain many phenomena which were associated with microparticles, small particles. Now, this failure of classical mechanics in explaining the black body radiation spectrum, the photoelectric effect, the stability of the atoms, it was removed by Max Planck, who proposed the Planck's quantum hypothesis. Now, according to Max Planck, a body consists of large number of molecules which are continuously oscillating or vibrating about their mean position. Hence, these molecules can be considered as molecular oscillators. The molecular oscillators do not possess continuous energy. They occupy those energy states which are having certain fixed or discrete energy, and this discrete energy was in multiples of E is equal to h nu, where h is the Planck's constant and nu is the frequency of radiation that is either emitted or absorbed. So, the energy of a molecular oscillator is given by E is equal to n times h nu, where n is the quantum number that determines the energy state that is occupied by the molecules. N can have value, n is equal to 1, 2, 3 and so on. Now, when the molecular oscillator makes a transition from one energy state N1 to another energy state N2, then the black body emits or absorbs energy in multiples of fixed amount E is equal to h nu. And remember that this fixed packet of energy E is equal to h nu is called quanta. So, whenever there is a transition of molecular oscillators, the energy absorbed or emitted, it will be in multiples of quanta. E is equal to h nu. So, energy absorbed or emitted is equal to delta n times h nu, where delta n is equal to n2 minus n1. Thus, according to Max Planck, energy emission or absorption is not a continuous process. Energy is absorbed or emitted in multiples of fixed unit called quanta, and one quanta is equal to E is equal to h nu. Now, based on this concept, on this Planck's hypothesis, Planck derived the expression for energy intensity emitted in the black body radiation spectrum, and the energy intensity emitted was given by U nu d nu. This is equal to 8 pi h upon c cube nu cube d nu upon e raised to the power h nu upon kt minus 1, which is given by equation 1. This is the energy emitted within the frequency range nu and nu plus d nu. In this small frequency range, the energy emitted is u nu d nu. Now we know that frequency into wavelength is the velocity of light. So if we make this substitution in equation 1, we get the energy intensity emitted in terms of wavelength lambda, and it is given by u lambda d lambda. This is equal to 8 pi hc upon lambda raised to the power 5 d lambda upon e raised to the power hc upon lambda kt minus 1. So both equation 1 and 2, they represents the Planck's law of radiation in terms of frequency and wavelength respectively. If you plot a graph of Planck's law versus wavelength, then we get a figure which is shown in this particular slide. And remember the experimental curve of the black body radiation spectrum. It is having a nature as shown in this particular figure. Now if you plot the Wien's law and the Rayleigh-Jeans law, then we get the figures as shown in this slide, and observe that the Wien's law was valid only at lower wavelength side, and it failed to explain the black body radiation spectrum at higher wavelength. If you take the case of Rayleigh-Jeans law, it was valid only at longer wavelength, and it failed to explain the black body radiation spectrum at lower wavelength. See the experimental curve. At lower wavelength, the experimental curve tends to 0 as wavelength lambda tends to 0. The emitted energy intensity should also tend to 0, but according to Rayleigh-Jeans formula, we see that the energy emitted, it goes to infinity at lower wavelength. So this disagreement with the experimental observed curve, it was called ultraviolet catastrophe. See here the same figure, ultraviolet catastrophe. It is the disagreement of the Rayleigh-Jeans law at lower wavelengths lambda. Now according to failures of the classical mechanics, we have seen that the Wien's law can explain the black body radiation spectrum at lower wavelength, but it fails at higher wavelength. The Rayleigh-Jeans law can explain the spectrum at higher wavelength, but it fails at lower wavelength. But Planck's law and the experimentally observed or obtained black body radiation spectrum, we have seen that both the curves are very similar in nature. So this slide shows the similarity between the experimental curve and the Planck's law. See both the curves, they are very similar in nature. While the curves for Wien's law and the Rayleigh-Jeans law, they could partially explain the experimentally obtained black body radiation spectrum. So, similarity between the Planck's law curve and the experimentally observed curve, this forces us to think whether the Planck's law can completely explain the black body radiation spectrum. So Planck's law can explain the black body radiation spectrum both at lower wavelength as well as at higher wavelength. So if it completely fits with the experimentally obtained curve of the black body radiation spectrum, then at lower wavelength, Planck's law should convert to Wien's displacement law. Why? Because at lower wavelength, the Wien's displacement law was valid. It could explain the black body radiation spectrum. So, at lower wavelength, the Planck's law should convert to Wien's law. And at higher wavelength, we have seen that the Rayleigh-Jeans law was true. It was valid and it could explain the black body radiation spectrum. So, at higher wavelength, the Planck's law should convert to the Rayleigh-Jeans law. If this is the case, if this is satisfied, then we can say that the Planck's law is completely fit with the black body radiation spectrum and it can explain that spectrum. Now see the case. At higher wavelength, we have got the Planck's law, which is given by this equation, u lambda d lambda. This is equal to 8 pi hc upon lambda raised to the power 5 d lambda upon e raised to the power hc upon lambda kt minus 1. Now if you take the case at higher values of wavelength lambda, then the ratio or the quantity hc upon lambda kt is a very small value, and if it is a small value, then the exponential term can be expanded as shown in this particular equation. This is simple. To e raised to the power x is equal to 1 plus x square upon factorial 2 and so on. But remember, this expansion takes place only if the value of x is small. So in this particular case, hc upon lambda kt is having a small value. So we can expand e raised to the power hc upon lambda kt in the following manner. Now, as hc upon lambda kt is a small value, we can neglect the higher powers of that ratio. So retaining only the first two terms, we retain only the first two terms and put it in the equation for energy intensity emitted. And if you make the calculation and rearrangement, then this equation reduces to u lambda d lambda is equal to 8 pi kt upon lambda raised to the power 4 d lambda. And remember, this is the Rayleigh-Jeans law. So what have we obtained? That at higher wavelength lambda, the Planck's law gets converted to Rayleigh-Jeans law, and the Rayleigh-Jeans law could explain the black body radiation spectrum at higher wavelength. So we can conclude that the Planck's law can also explain the black body radiation spectrum at higher wavelengths. Now see the case at lower wavelength. The energy intensity emitted is given by equation for u lambda d lambda. Now, if you remember the black body radiation spectrum, then we have noted one thing, that the energy intensity u lambda is maximum corresponding to certain wavelength. Lambda is equal to lambda m, and after that the intensity decreases. Now we take a concept in mathematics that if a function is having a maximum value at certain point, then its first order derivative at that point, it should be equal to 0. We are using this concept. So we have seen that the emitted energy intensity U lambda had maximum value at lambda is equal to lambda m. So the first order derivative d lambda of U lambda at lambda is equal to lambda m, according to the condition of maxima, this value, the first order derivative at lambda is equal to lambda m should be equal to 0. That is represented by our equation 4. Now if that is the case, taking the log of equation 2, that is the Planck's law on both the sides, you get the expression shown in equation 5, and if you differentiate it with respect to lambda, we get an expression shown by equation 6. Now remember the condition for maxima, d lambda of U lambda at lambda is equal to lambda m, this is equal to 0. So use equation 4 and 6. So if you use the equation 4 and 6 and replace the lambda by lambda m, then you get the expression that is 7, equation 7. So make a substitution, put hc upon lambda m into kt is equal to x. So the equation, it simplifies to equation 8, that is 1 minus x by 5 e raised to the power x, this is equal to 1. Now solve the equation 8 by trial and error method. On solving this, we get x is equal to 4.965. And what was x? X is equal to hc upon lambda m kt, and that is equal to 4.965. So just make the rearrangement. We get lambda m into t, this is equal to hc upon 4.965 into k. K is the Boltzmann constant. If you put the values of all the constants that are involved here in SI unit, finally we get lambda m into t, this is equal to 0.292892 into 10 raised to the power minus 2 meter Kelvin. And remember, this is the Wien's displacement law. Equation 9 is the Wien's displacement law. So what have we obtained? That the Planck's law of radiation converts to Wien's displacement law at lower wavelength lambda. And remember, the Wien's displacement law could explain the black body radiation spectrum at lower wavelengths lambda. So we can conclude that the Planck's law, which converts to Wien's law at lower wavelength lambda, can also explain the black body radiation spectrum at lower wavelength. Now since the Planck's law of radiation, which was based on the Planck's quantum hypothesis, it could explain the black body radiation spectrum both at lower as well as the higher wavelength. So it is said that it is completely fit with the black body radiation spectrum, or the Planck's law is completely fit with the black body radiation experiment, and it can explain the black body radiation spectrum. So that's all about the Planck's law. Have a nice day.